This project demonstrates an understanding of autonomous vehicles along with the programming and coding of a JetBot. A team of 3 mechanical engineering students, Shane, Chris, and Tyler, worked together to learn and demonstrate 6 objectives during the ME435 autonomous vehicle module to select and execute the desired functions. In Lab 1, the main objectives were to learn the basic syntax commands of Python and use this to control the motion of the JetBot. The JetBot uses Python to control its motor functions, forward-facing camera, and communication with the computer software. The first task was establishing the bias in the JetBot's mechanical system. Unequal motor power will cause the robot to veer over the desired track line in one direction or the other. Working with kinematics of the robot will allow the team to understand the metrics of the motor and adjust for bias in the motor power. Lab 2 introduced new mechanics to the JetBot's autonomous capabilities, line following, and sign recognition. The group worked to modify images captured by the JetBot's onboard camera from RGB to HSV color combinations. Code was created to work in conjunction with the HSV colored images to overlay a trace line onto the live image captured from the onboard camera. Code was then created to ensure the trace line matched with the track center line as it followed along the track using a PID controller. The heading angle of the robot was calculated and displayed to show how far the robot needs to adjust to remain on the center line. The group also designed the sign recognition software during this lab. The group began by taking several images of 3 different possibilities the robot could encounter: no sign, stop, and speed. These images were processed and a model was trained to allow the robot to recognize differences between these signs to account for the change in scenery. This model was then used with kinematics to allow the robot to move while there is no sign, to stop once there is a stop sign in view, and speed up when the speed sign, in this case a yellow sign, is seen.
Lab 3 introduced a new perspective into a UAV track, overhead cameras with April tag processing. To use the overhead camera, calibration needed to be performed to adjust the image from the camera from a fisheye view to a flattened 2D view using distortion matrix. Once this matrix has been computed, the April tag can now be accessed and the location of the robot has been determined. By now having a layout of the entire track and the location of the JetBot, an algorithm was created to find the shortest distance to another selected location anywhere on the track. A probabilistic roadmap was created using similar HSV modifications and nodes were placed on the road of the track. Using transformation matrix, the robot could be sent a location on the track to determine where the optimal next node is and what action needs to be taken to reach that node.
A flowchart was created to combine the 6 required tasks for the fully autonomous vehicle, beginning by labeling the JetBot name and IP as well as the CameraBot name and IP into the robot communication network to allow for connection between the robot code and the global camera. Now with access to the camera, images of the signs can be taken from the robot to create the trained model as well as to have a live camera feed. With the live camera feed, the robot can now recognize signs through the trained model, as well as with the path following and the PID controller. It could determine the live images with tracer lines and heading angles for the robot to follow. The path planning is done separately by converting a real image to pixel scale, as well as a mapped image in JPEG form for the robot to transpose its image across. The output is the shortest path determined, as well as inputs for the robot's kinematic commands such as left, right, and straight. The 3 of these combine together into the robot's fully autonomous motion. Due to time constraints, only a select few tasks could be implemented into the final production of our autonomous vehicle. The group decided to focus mainly on robot kinematics, sign recognition, April tag locations, and camera calibration. The culmination resulted in a combination that approached the desired result. The JetBot uses the April tags to determine its initial location through image capturing. After a desired amount of time, the robot begins moving using kinematics along the track if no signs are present. Once the robot encounters a sign, the robot's live camera will process the image and determine what sign is present and what actions need to be taken. If a speed sign is present, the robot will speed up for an allotted time, and if the stop sign is seen, then the robot will stop and capture a second image. After 2 images are captured from the overhead camera, calculations are done to determine the total distance traveled by the robot, how long it took to reach this distance, and the average speed of the robot is then calculated. These tasks combine together to create an autonomous vehicle that will become the forefront of humanless driving.